Okay, so long time ago, once upon a time, like as soon or as far ago as last year, we used to go through the entire history of the atom. And what I mean by that is we used to go from all the way from um, the Greek philosophers, and we used to be able to say, like, there was a guy named Democritus who basically was the first person to use the word atomos, which means indivisible. And then or yeah, which means yeah, indivisible. And then there was another philosopher that talked about some other things. And then there was a school teacher who read a bunch of research and said that all atoms, here are the 5 things that we know about all atoms. But the issue with those things is that it's not that they were wrong, it's just that they were information that was based on observation and not information based on collected data. So in this we're starting this year by talking about all that we know about the atom based on the data that we've collected about it. So the first thing that we need to talk about is the model of the atom itself. And this is the model of the atom that you're probably most familiar with. It does have its own special name. It's called the Bohr model. But in reality, it's a good representation of an atom, but it's not 100% correct. So this is a good representation of an atom, but it's not 100% correct. Okay. Now, for those of you that are just kind of getting started here, you had the long weekend. This is the part where you're probably taking some notes and not looking at your crotch. There are parts of the atom that you might be familiar with. These things right here on the outside of the atom, they're called electrons. Then we have the middle of the atom, and in the middle of the atom, we have protons. And we also have, let's say, we'll call those the neutrons. So those are the basic parts of the atom. As a result of those being the basic parts of the atom, you have to understand that the atom itself, the protons, neutrons, and electrons, are also made up of even smaller particles like quarks, neutrinos, and flavors, but we're not going to really spend a lot of time talking about them because for the scope of this class, they're not super important. So I want you to take a second to tell me what you know about electrons. Because I know you know something. Some of you know something. Anybody know anything about an electron? Does an electron have a charge? Do we know what the charge of the electron is? Do we know what the charge of the electron is? There you go. Thanks for playing. The electron, hey, thank you for taking a chance, is negatively charged. Okay. Do we know anything else about the electron? There you go. The electron is outside of the nucleus of the atom. And the one thing that you might not know about the electron that we need you to know about is the mass of the electron. And we would say that the mass of the electron is negligible. Now, I'd like to try to give an example of what negligible actually means. So if you look at any of the cars outside there, right, in the parking lot, many of those cars probably have a weight of somewhere around 1,500 to 2,000 pounds, depending on the car. So if I took the engine out of any of those cars, the mass of the car itself would decrease significantly. Does that make sense? But if instead of taking out the engine, I took out like one singular screw or bolt, that would not change the mass of the car very much at all. As a matter of fact, it would change the mass of the car so little that it probably still would be about 1,500 pounds. So when we say something has negligible mass, it's really in comparison to the system at hand. So in the case of the car, one screw would have negligible mass in the whole mass of the car. But in the case of the atom, the electron is so small that it does not contribute to the mass of the electron because the electron is super duper tiny. Does that make some sense? Okay. So, the next thing I'm going to show you is a video. No. Is a video that sort of describes
here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thompson, who became the director of this, the old Cavendish laboratory. In 1896, Thompson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen, which glows so you can see the beam. Now, this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thompson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thompson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thompson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. Like apparently Shakespeare, say my use is great because I am so small.
The electron was the first discovery of a fundamental particle, and it is interesting to realize that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thompson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thompson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thompson's that proved him wrong.
So this is one of my wife's favorite science videos of all time, because as he talks more and more about his muffin, it becomes increasingly obvious that he's saying the word muffin for muffin. Long story short, Thompson came up with this idea of what an atom would look like, and he thought that the atom was essentially this sphere of positive goo, the muffin, with negative particles just kind of sprinkled inside of it, the chocolate chips. Okay, so in our world, what we knew about the electron is essentially based on what we call this cathode ray tube experiment. And a cathode ray tube, so that device that he showed you, that glass, that piece of glass where that was like hollow inside, is essentially a souped up version of what old TVs used to be made of. So tube TVs are those big fat computer monitors. You may remember those from like, I don't know, maybe 3 years ago in the computer lab. So the point is those big fat monitors have this giant cathode ray tube inside of it, and they basically operate the same way. There's a particle that is shot through the cathode ray tube. It becomes excited, and then when it hits the end of the cathode ray tube on that screen, it kind of makes an image or a picture show up. In this case, the image or picture that shows up is a green dot. Okay, and what Thompson's experiment was that as he increased the charge or the amount of charge or the intensity of the charge at the metal plates on the sides of the cathode ray tube, he noticed that the beam of electricity was always bending to the same side, and it was always bending toward the positive side of the plate. And when it was bending toward the positive side of the plate, Thompson deduced that there must be a particle inside that electric beam that is negatively charged. And so those particles were called electrons. So that's how we know what we know about the electron. That's the experimental evidence that supports the fact that all atoms have some negatively charged particle inside of them. Which then brings us to talk about, what do we know about our proton? So, what do we know about a proton?
Positive.
Protons are positively charged. What else do we know about a proton?
It's the inside of the
It's located in the inside of the nucleus of the atom. And the other thing that we do know about a proton is that protons have a mass of 1 AMU. Now, AMU means atomic mass unit. Now, I'd like to try to quantify what that means for a second, so that we know, according to the periodic table, that the mass of hydrogen is essentially 1 gram. Okay. But what makes up a hydrogen atom is a singular proton and one electron. So and that's the simplest way to describe what an AMU is. An AMU is the mass of one proton, basically. And the simplest way to describe that would be that if hydrogen has a mass of 1 gram, what that really means is that it's the mass of the one proton, because that's the only thing that hydrogen has. A more complete answer is the fact that carbon, which has a mass of 12, is made up of 12 protons. And if we divide that into, if we basically say that one proton is equal to 1/12 the mass of a carbon atom, then we have the mass of a proton. But that's too much complicated business, so we're going to keep going. Now, how do we know what we know about a proton? Well, there's a video clip for that, and we'll show that in a second. And hopefully this works this time. Nope.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thompson, who became...
There we go. There we go. Let's watch this one. Hopefully this one works this time.
Time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing them as a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at the target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounced back into our detector.
Okay. So that was a quick representation of what Rutherford and his colleagues actually did in terms of how they collected the data. What is really important to understand is that the energy was a beam of positive alpha particles, and they were shot through a piece of gold foil that was roughly 1 atom thick. Now, the other thing that's important to understand is, like, when you think about foil, a lot of times you think about aluminum foil. And aluminum foil is pretty thick itself, but gold foil, like even the craft gold foil that you might find at like Michael's or whatever, is really, really thin and really, really delicate. And that's very similar to what this is, even though this is actually even more thin than that. Scientists would then shoot these alpha particles into the gold foil, and they expected to see all of the alpha particles show up on the other side. What they found out, though, was that not all of them showed up on the other side. Some of them went off on an angle a little bit and were deflected away from where they predicted they would be. This is the equivalent, I always think, of taking like a bucket full of marbles and standing in front of a volleyball net and throwing that bucket through of marbles at the volleyball net. In theory, every single one of those marbles should go straight through and hit somebody in the face that's standing on the other side. But we also know that because a volleyball net has like places where the netting crosses, there is a small chance that 1 or 2 or even more than that of those marbles would hit that intersection and be deflected off to the side. Does that make sense? So that's how, so prior to this particular experiment, we thought that all of the particle charge was basically, or all of the positive charge was basically a just spread out throughout the entire atom. But what we found out was that the positive charge was centered in the center of the atom. So there has to be a positively charged center in an atom. And that positively charged center has protons in it. So that's where the proton is located. Another thing that the video touched upon is that J.J. Thompson had theorized that the atom itself was this giant goo of positive stuff, right? And Thompson, the person who did, or Rutherford, the person who did this experiment, basically came out with the knowledge that the atom itself is mostly empty space. So mostly empty space. So what I mean by that is that if the center of the atom itself is this positively charged nucleus and the electron is like way out here, okay, there are no particles in between the positively charged nucleus and the electron itself. So like when you open up the refrigerator at home and you're like, oh, there's nothing to eat. Well, there's just nothing that you want. You could eat a ketchup sandwich if you really wanted to. Gross, but you could. You could eat the leftovers from last night, but you don't want them, right? Very, very rarely does anybody open the refrigerator and there's nothing in there. But in the refrigerator of the atom itself, when you open up the atom from the electron, which is way, 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 way out here, to the nucleus, which is over here, there is nothing. Actual nothing. Like there are no more particles there because there aren't particles small enough to be there, which is kind of weird to think about a little bit. So we're going to move on. What do you know about the neutron? Anybody? Neutrons have a neutral charge. Do we know anything else about them? They are in the nucleus of the atom. And the other thing that you may or may not know is that neutrons do have a mass of 1 AMU, or atomic mass unit. So again, what I kind of said at the beginning of the hour was that this information, or how we know what we know about the atom, is based on experimentation and data that we collected. So here's what we thought, but it's not necessarily true. We thought that since all atoms have protons, okay, if we had an atom that, say, had 10 protons in it, then 2 atoms of, say, 3 protons and 7 protons should have equal masses. Does that make sense? Because if each proton is 1 atomic mass unit, right? If I have an atom with 10 protons in it, it would have an atomic mass of 10, right? And if I had an atom with 3 atomic mass units, 3 protons, and an atom with 7 protons, then those 2 atoms should have the same mass as the 1 atom with 10. And what we noticed was that was not entirely true. So collected data proved otherwise. Now, so there was some collected data to support this, and the collected data that would support this was the fact that we knew that certain atoms had a specific number of protons, and yet those atoms' masses did not match up. So what I mean by that is that lithium, for example, has 3 protons, but its mass is actually 7 atomic mass units. Helium has 2 protons, but its mass is 4 atomic mass units. So this information said that there had to be another particle that had some mass, and that particle could not have a charge. And it's important to understand that because we know that all atoms themselves are neutral. That is, they don't have a charge. So if we have some negative things and we have an equal number of positive things, then they have to be neutral, right? But if there's another particle in there that had a charge, that would offset everything, and then that wouldn't make any sense. So let's review. Subatomic particle. We had electrons. We had protons. And we had neutrons. Electrons are located where now? Outside the nucleus of the atom. What about protons? Inside the nucleus. What about neutrons? Thank you. What about the charge of electrons? Thank you. What about protons? Thank you. And neutrons, neutral. Mass of protons, mass of electrons. According to our notes, they were negligible. Mass of a proton, 1 atomic mass unit. And the mass of a neutron, also 1 atomic mass unit. Okay, so we've covered a little bit today of material, okay, and that was a very, very basic introduction to how we know what we know about the inside parts of an atom.